So welcome back to this session on Cornerstone Ideas in Material Science and Engineering, Content cum Pedagogy. So in the last class we discussed ideas to do with Socratic learning. So primarily the Socratic method, wherein leading questions are used to create the necessary scaffold for the student to sort of discuss with one another and develop the knowledge framework that you want them to develop. And in that context, I also talked about the Harkness table, which is essentially the table wherein you create an environment wherein they can see one another, talk to one another in a very open manner, and as a consequence create a Socratic circle. It's also called the Socratic seminar, wherein they can maybe even ask questions to one another. You ask them a question and then there are leading questions or information that is coming forth. You do this back and forth till they sort of have the necessary information at hand. So here are some questions to ponder, and it's not just a question. So these are some questions that I would like us to ponder about, and that has to do with the following. Is the Socratic method or related ideas like Socratic circle or Socratic seminar or Harkness table. Harkness table is a relatively modern idea. Helpful in creating ontological / knowledge maps? The answer is absolutely yes. You saw it in the last class. In fact, in the last class, the students did an exercise wherein they were told to recollect whatever was taught to them over the previous 2 hours, and they made a knowledge map, and you saw that it was fairly well constructed. So they had a fairly good understanding, and it involved a certain degree of Socratic intervention in the sense that I asked them questions. Do you think this is connected to this connected to this? And that brought about new branchings in the knowledge tree which otherwise did not exist. So maybe links they did not realize, they started realizing because of the questions that were asked and so on. So the answer to this is yes, it does indeed help. The next thing is, can the Socratic method be used to make the student self-aware? This is very important, of their schemas so that they can build content on it. This is very, very essential. So a good learner is somebody who sort of understands where they stand so that they can sort of top up information accordingly, learning experience accordingly, and so on. But if they do not even have a schema of what they know, it becomes very difficult for them to learn and for a teacher to teach them. So a good question to ask is, can Socratic method be used to make the student self-aware of their own schemas and where their current knowledge stands? I think it is possible. In fact, in the context of education, increasingly people think about some kind of assaying of where the students stand. For instance, you could give a diagnostic test even before you start your lesson, because there may be some prerequisites for your course, but the students may not have those prerequisites, or they may not meet those prerequisites, in which case you could give them suitable reading material or maybe even have some preliminary discussions in the class. But you wouldn't know whether you have to do either of those unless and until you had a diagnosis on your students. So it is helpful to have a diagnostic test. Now there are some people who would like to do these diagnostic tests in a very, very systematic manner. For instance, they would print out quizzes and ask students to fill out a Q&A and so on and so on. Another way of doing it is Socratic. You ask students, go around, check what their level of comfort is with respect to the concepts that are being discussed, whether they have the necessary prerequisites. And once you are comfortable about their awareness levels at this particular moment, you could pitch further questions and create a scaffold around it. So one of the important elements to creating the scaffold, an effective scaffold as a consequence, is knowing where your students stand. And that requires you to ask them some questions and assess the questions. And this could be done orally as well. So a particular concern that some students, some teachers might have has to do with especially students who are falling off cracks, who might not have the background that is necessary, who somehow are taking your course, but they really do not have the necessary scaffold to begin with. So in which case a one-on-one interaction is actually very helpful in sort of seeing what needs to be provided so that you could at least give the pointers. You might not be able to solve all their problems, but you can at least give them pointers regarding what they could do to come up to speed. So that is one way of thinking about it. So I use Socratic method, by the way, to assess students. So whenever I, let us say, see a student who is falling off the crack, it could be for a wide variety of reasons, but my first assumption is usually that their conceptual base has something that is lacking. So I tend to talk to them and then find out what might be lacking as far as their backbone is concerned, their academic backbone is concerned, and if there is a reading intervention that can be recommended, I usually recommend that. So that is one way in which one could do this, sort of making sure that students don't fall off cracks. Of course, you can never ensure 100%, it's always a challenge, but at the same time there is certainly a scientific method by which you could intervene and perhaps improve the possibilities associated with student performance. So connected ideas are assimilation and accommodation. Assimilation and accommodation wouldn't even happen if you did not have an understanding of where your students stand. So you wouldn't even be able to give the right kind of information if you did not know where they stand. Because new information goes, you have old information, already pre-existing knowledge, new information goes, and it has to be assimilated and then accommodated. Now if the new information that goes doesn't fit into the schema of the pre-existing knowledge, then there is no new knowledge level that basically emerges from that exercise. And as a consequence, this is rather important. So the idea that I gave, which is to do with maybe intervention, perhaps a reading intervention based on your discussion with a student who might be falling off cracks, comes from Piaget's ideas. That is, there is assimilation, accommodation that is important, and for that to happen, your pre-existing knowledge and the student's pre-existing knowledge needs to be taken into account. Now what if students involved in this exercise have improper note-taking skills? Now this is another very critical question. Okay, so there is again a lot of evidence that note-taking is a skill, and there is a science about it now. For example, there are many well-established note-taking skills, including the Feynman note-taking skill, the Cornell note-making, and so on, so on. So these are techniques that enable the student to structure information in a particular manner, and that as a consequence enables them to learn better, understand and assimilate better. So there is a science about it which I won't go into for this session. Maybe in one of the subsequent sessions we will talk about the recent most developments as far as note-taking related studies are concerned. So what are the interventions that could be enabled? You talk to students about their note-taking skills. Look around, you know, when you walk around, see what their note-taking habits look like. Is it structured? Is it very ill-structured? Ideas that are totally incongruent are brought together and so on. If that is the case, the student is certainly not learning. They are probably remembering. They are memorizing. They are not necessarily creating a schema for themselves, and that is very problematic. So why is note making important? Because it's a representation of what is there in the student's mind. And if that representation is very improper and very poorly constructed, it is usually evidence that the student is not necessarily having the right learning habit. So note making habits as a consequence can be correlated in some sense with learning habits, and there is quite a bit of literature about this right now. In fact, for the last almost 60 years, educators have been asking this question about what is the quality of notes that my students make and how does it correlate with their learning. And there is a lot of correlation that is actually established. So typically well-performing students tend to have very good note-making skills, very structured way of distilling out lecture content, and as a consequence there may be some value to teaching our students how to make notes. So that's an area by itself and I won't go into it as of now, but I might walk you through some literature and some recent developments in due course. So what if there are students who are introverted? Now this is very important. A Socratic setting is something that requires a lot of discussion, right? Even active cooperative learning requires a tremendous amount of discussion. However, from my experience and also the experience of other educators who really care about creating a classroom environment where all students feel like they should be true participants, there is evidence that introverts in particular are very uncomfortable with the active cooperative learning setting. Now, so especially the way it is popularized, the way it is made very dialectic, very discussion oriented, discourse oriented, the more extroverted student might raise the hand more often, might talk more often, might participate more often, might talk to the neighbor more often and so on, while the one that is more introverted would rather prefer to think on her own or his own, and things of that sort might open their mouth only after a certain thought is crystallized in their mind and so on. So what do you do in such a situation? So there is no easy answer, and it is still an area of research, by the way. And one person who has studied this, she is herself somebody who claims to be a highly introverted person, but she's somebody who studies it, a person called Susan Cain. And she has published a book recently, Quiet, the Power of Introverts in a World That Can't Stop Talking. There are some segments in this particular book that has to do with how to interact with introverts and how introverts can interact with the world around them. And there are some lessons for the teachers also, who might have to deal with introverted students, who might have to work with introverted students and so on. So there is evidence that they need a different kind of space. Now, it is not yet clear, and certainly literature is not yet clear about this, whether this Harkness table method, for instance, would work very well for introverts, because they prefer different spatial settings, and they prefer to, by and large, study on their own. They do not prefer discourse. They might be very good listeners, but they may not participate. So one way in which we could actually make it friendly towards introverts might be, number one, also promote out of the classroom education, perhaps wherein they could come meet you, number one. That is certainly one possibility, wherein you could have a more one-on-one interaction. Number two, emphasizing reading and, let us say, classroom participation in by and large equal measure. They might participate occasionally, in which case you could sort of see what their contribution is and value it just as much. So trying to normalize the contribution just as much, because there's a tendency to sort of value the extroverted person's contribution, because he or she would be talking, and that's the world that doesn't stop talking, okay? So they would be talking. It's more easy to measure their contribution. It is harder to measure the contribution of introverts. But I think the science and debate about this is still very underdeveloped, and there is a lot of scope for work in this area. A personality psychologist who is looking into this particular problem, not explicitly in the domain of education, but who has written quite a lot about it, is one Professor Jordan Peterson from the University of Toronto. His writings might also be rather relevant, but this is the easiest book as far as I am concerned, and it's rather recent, Susan Cain's book. So with that as the backdrop, let us proceed. So to summarize, teaching is something that needs to be thought about in great detail, because your student demographics, your student spectrum can be very different, and based on that there might be some degree of creative interaction with the student that will become important. Maybe even a non-conformal way of interacting with the student. By that what I mean is getting the student to meet you in office hours, for instance, or giving them a reading package, for instance, a reading package that others may not be required, but they might be encouraged to read. So providing necessary pointers to the students who might be falling off track, or students who do not fit into this scheme of learning and teaching that we are talking about. There is a related challenge and something that is totally under-researched, because I was looking at this problem and I did not find much literature at all about it, and that is, what if a teacher is introverted? It is extremely challenging for the teacher, and there is absolutely little or no literature about it. What can be done to make sure that it's still a win-win situation? Classroom is still a win-win situation. There are extraordinary challenges associated with it, and I find it fascinating. And if there are viewers out there who are interested in looking at this as a research problem, I would be happy to talk about this, okay? And I'll be happy to interact with you in this particular regard. So we discussed the importance of note-making skills, and I told you that there's a science about it as of now. The two prominent note-making skills that are out there, or note-making techniques that are out there, are the Feynman note-making technique and the Cornell note-making technique, and they are both sort of available. Large number of educators employ them. Large number of educators talk to their students about note-making in this context. And what about students who do not fit into our active cooperative learning settings? That can become a challenge as well. And then, can you use the Socratic method in order to assess your student learning levels and also their pre-existing schema? The answer is absolutely yes. And the answer to that by and large also comes from Piaget's work on assimilation and accommodation. And is the Socratic method helpful in creating a knowledge map? The answer is a thumping yes, no question about it. So here is a problem. So I have a linear chain, and somehow I have managed to make these linear chains almost monodisperse. Okay, somehow I have managed to do that. And here is another linear chain, and here is another linear chain, and another linear chain, and so on. And what I do is I basically find ways to link them up. Okay, more or less in a structurally self-similar manner. Okay, so this is a polymer chain. So what kind of a chain would this be? Linear, right? So I have a linear chain. This is also a linear chain, but I have managed to stitch it together, and this is also linear. However, I have managed to stitch it together using this to give rise to a ladder-like structure. Okay. Now, can this be done? The answer is yes. Okay. It turns out that you can build ladder polymers from linear polymers. Okay. So there are people who actually do this, and the technique to do this is something called radical polymerization. So you can use something called radical polymerization. So can you write this down and read about it? And a good question to ask yourself is, I have linear polymers, how do I convert into ladder polymers? By using radical polymerization. All of you know what radicals mean? So prima facie it makes sense. Suppose I want to actually make a branch here, I can create a deficiency of an electron here, deficiency of an electron here, so that they could pair up in a covalent manner. Deficiency, deficiency, pair up, deficiency, deficiency, pair up, and that way I would have a ladder. So that's the idea of radical polymerization. It's as simple as that. So you just have to structure it out, you know. Now I have this polymer, and then I have another polymer. So I'm going to compare this with another polymer. So it's the same composition, the same linear polymer, but that is structured like this. Which of these two do you think will have a higher TG? So please discuss with one another. Higher TG. So please discuss with one. So you will. So here the big difference is you have a covalent bond. What is the bond here? Van der Waals. That is the big difference. Correct. It makes sense, right? So which one will be more rigid? Lower one. So typically you can improve the rigidity of a polymer that looks like this by taking this route. Polythene, this is really one of the strategies that you can use for making it more and more rigid. So there are so many polythenes that are out there in the market, isn't it? So the question is, how can I actually go from this to this so that it can take more and more load, so that the load bearing capacity improves? How do you improve it? And what is the technique? Okay, so this is the most standard way in which that problem is solved. So load bearing polythenes can be actually made increasingly by using this technique. Now this idea of crystallization is very interesting because does it exist in biology? I mean, see, biology has a lot of polymers, right? Your skin has a lot of polymers. Polymeric substances are there very widely. Cotton is a polymer. And in fact, very interestingly, cotton has a fair degree of crystallinity. All right. So not just cotton, silks, the way in which silks are extruded, all right, they actually give rise to a certain degree of crystallinity. Clearly, the sheen of the silk will actually be determined by that. You know, not very far from here is Kanchipuram, which is very famous for silk saris. So, in fact, a large number of processes are geared towards ensuring that there is a certain degree of crystallinity in this siliceous, not siliceous, in this silk based fibers and so on and so on. Okay. So if you investigate the processes that are involved, it has to do with crystallinity and crystallinity modification to a large extent. So the science behind it has to do with crystallinity. So even in the world of biology, crystallinity plays a very important role. In the world of fabrics, crystallinity plays a very important role, and so on. In this context, I wanted to introduce a puzzle, a very interesting puzzle as far as I am concerned. You know, our DNA. So human beings have chromosomes, right? How many chromosomes do human beings have? 23? 23 or 46? Or 23 pairs? 23 pairs. So each one of us, unless you know, we are having a genetically different composition or some such, it's just a possibility, by the way. It turns out that there are 23 pairs in the case of an average normal human person. Okay, so there are 23 pairs. Now each of those chromosomes are made up of dash DNA. If I unwind that DNA, it is several hundred meters long. You know, it's very, very, very long. Unwind it. But you wind it up, make it very, very closely packed, and you have something that can be seen only in a particular stage of cell reproduction under a microscope. You cannot even see it otherwise. It's an amazing thing. You know, the density of packing. And that is actually an example of a polymer packing. Highly dense, highly crystalline. The level of crystallinity you don't see elsewhere. To engineer it would require a lot of effort. And as I told you, between 35 to 50% crystallinity if you achieve in an engineered system, that's a pretty amazing thing. So, but here is a situation wherein you have a chromosome and it has DNA that is very, very beautifully stranded together, that is structured, and it's a highly crystalline object. How is it possible? What lesson can we learn from that from an engineering standpoint? You know? So here is a biological example. It's a fascinating thing, isn't it? You know, something that is this long is folded to the point that you can't even see it. It's a pretty amazing thing. That means you can actually pack a lot. There is tremendous packing efficiency in the case of the DNA. And we never achieve something like that in an engineering system. But can we do that? Number one. Number two, what hint do we get from nature about crystallization as a consequence? So can you discuss this with one another? It's a very interesting thing, isn't it? Many of you might not have studied biology in your +2, but you don't need biology. This is really a physics or chemistry question in some sense, all right? And I want to connect it to material science and engineering. Do you understand the question? So what are some of your answers? What do you think is responsible for this level of condensation for DNA? It's actually called condensation technically. It's called condensation. Biologists wouldn't call it crystallization. They would call it condensation of the DNA material, all right? And it's for a very good reason, and I'll come to that, okay? But what is your argument?
So like they are thinking some radicals of nitrogen place.
You think it's some kind of a real chemical reaction? Actually, it is not. It's mostly secondary bonding. In fact, the secondary bonding plays an important role in creating the helix, and then eventually all of it is actually coming together to give rise to a chromosome. All right, so and it's actually getting folded, you know, through the chromosome. So why would that happen? What's your answer?
The helical structure might help.
Yes, it does. You're right. You're right. It actually does. What is interesting is in the cell nucleus, it happens like this. Every cell of your body is actually doing it. But if you take the DNA out, you cannot do it. You know, so DNA crystallization becomes challenging outside of the cell. But inside the cell, it's happening all the time. All the time. It's pretty interesting as far as I am concerned. And if you look at it as a polymer problem, it's very interesting. And I would like to sort of learn some lessons from it from engineering standpoint. How would you actually engineer a polymer to get it more and more crystalline and so on? So that's why I started reading about it. And here are some lessons, okay? So it turns out that DNA in general has almost no bulky side chain. So there's no steric hindrance towards its condensation. That is number one. If there is steric hindrance, then you will always lose crystallinity. Number two, it turns out that this DNA condensation that I'm talking about is facilitated by proteins. So it is not a passive process. When you are nucleating and crystallizing in your laboratory, usually you are doing it through some slow cooling and so on, and you want it to be a passive process. You know, you basically are not necessarily intervening. There is no robotic arm that is going and arranging this protein in a very specific manner or a DNA in a specific manner. But in the cell, there are actually proteins that do this. Okay, they are called scaffolding proteins. So we have used the word scaffold before in this class in the context of Vygotsky's scaffolding technique. This is different. So these proteins basically provide the structure along which this nucleation happens. So as a consequence, they are actually stitched together actively through the active participation of proteins. So it is the protein DNA interaction, the protein genetic material interaction that is responsible for this very close stitching of the DNA material, which really never happens in a real engineering experiment. But think about it. What would be the relevance of this from an engineering standpoint? And there is something remarkably similar that is there in the world of chemistry, mostly inorganic chemistry, and that is the idea of co-crystallization. A single crystal may not come out, but you have another crystal already, so that scaffolds this other crystal and then together they come out. Okay, so this is a little bit like that because the proteins have very specific interaction with respect to one another and use the specific interaction of these proteins with respect to one another and the scaffold they create as a consequence to stitch the DNA together. So it is almost like a co-crystallization event, and hence it is, biologists usually call it a DNA condensation, but you take it out of the cell, as I told you, it becomes very difficult for you to sort of crystallize DNA, and that's the reason why DNA crystallographic result was actually something that took time. People sort of knew how to isolate DNA in some sense, but they did not know how to crystallize it. It takes time. It's usually a very, very slow process. Typically, it's slower the process, slower is the cooling, better is the degree of crystallization that you actually get. And macromolecular architecture, there are some words I have written about it, some sentences I have written about it which might be relevant. So there is relative positions of various atoms with respect to the protein backbone, dispersion medium use, thermodynamic parameters including chemical activities of ions, rates of crystal growth determine the extent of crystallization. So this is true for DNA also. So the solution in which you are actually crystallizing matters. This is true for any polymer. The solution in which you crystallize matters, and hence the various chemical activities of the various ions that are present in it matters. The dispersion medium that you use matters, and also if you are providing any backbone, it's equivalent to co-crystallization, as I told you. So any backbone that you provide does matter. Semi-crystalline polymers are most often found. So semi-crystalline basically means it's not 100% crystalline. In fact, it's nearly impossible to find 100% crystalline polymers. In high molecular weight polymers, it is very hard to reduce amorphous region to less than 40%. So 60% is about the champion crystalline polymer that you would actually find. So I told you 35 to 50% is nominal. 60% is about the champion crystalline polymer that you would actually find. Now, when I say that 60% is the champion crystalline polymer, you would find what is the other part of the polymer? Amorphous. So, as a consequence, I have polymer, and this polymer, even the champion one, has a 60% max typically of crystallinity. And what is the remaining region? The other one is amorphous. Okay. Now let us think a little bit more about the amorphous part. Okay. Now here is an example of something called the fringed missile model. So let me give you some text that I have highlighted. Okay. What is polymer crystallinity? I have written a few sentences about it. And when you read this sentence, these sentences, and some of the sentences have been highlighted because that I think is important, make sense of this micrograph. So this is a micrograph, that means a microscopic image for all practical, or it's not really a microscopic image in the sense that it comes from an optical micrograph. No, it is microstructure, as you would imagine, of regions where there is some amorphous polymer that is basically coexisting with crystallite region. So this is sort of how it has been demonstrated, it has been shown. So let us make sense of this picture in light of this discussion. So the Socratic question for you is, read this stuff, okay, how does this correlate with this picture? You understand the question? You understand the question? Read this material that is provided and let us make sense of this picture. So let me see if I can lower this down a little bit so that you get to see the, yeah, this is good enough. So can you read and discuss especially the highlighted portion and make sense of this picture? So spend a minute reading, minute or two reading, then discuss for a minute or two and then let's make sense of this picture. Okay, so please discuss with one another and make sense of this. So I've written something here, now we have to make sense of this. So you have been provided some information, now we have to fit that information into some picture I have given you. This is called the fringed micelle model, and let's make sense of it, showing both crystalline and amorphous regions. So here, where are the crystalline regions? Where are the amorphous regions? What is the approximate fraction of crystalline region? How do you know that something is crystalline? What technique would you use to find out crystalline region vis-a-vis amorphous region? Okay, how would this correlate with some measurement that you could do? These are the questions that you could discuss among one another. Okay, but broadly, the question I am asking, the Socratic question is, how does this information fit into this? Okay, so please discuss. So you can identify, let's say, 3 points and say, this is the information, it fits into this picture in such and such manner. Okay, you understand the question? Yeah. So please discuss. So what do you think?
So for example, so these are the crystalline regions, these are the amorphous regions. So how do you know which portion is which? Like in XRD you will get just peak, some peak or some amorphous peak like that.
Oh, that is, XRD will give you bulk, no? For XRD will give you the diffraction pattern for the whole sample. Okay. Now, if I had to find out where crystalline region is and where amorphous region is, how would I do that? Can it be just any optical microscope? Impossible. No, don't even go towards electron microscopy. You know. No, we learned something about the properties of crystalline polymers. So this is the inverse question. Earlier I said, I have a crystalline polymer, what use could I put it to? Now I am saying that what are some of the properties as a consequence which I can use to study? Density, but density is also bulk measurement, no? So we discussed some things last time, right? What did we discuss? How does crystallinity impact, let us say, anisotropy in strength? But strength measurement is also bulk measurement. So from strength measurement, you wouldn't be able to say this is crystalline, this is amorphous and so on. Hardness measurement is also a bulk measurement. From that, you wouldn't be able to actually say that this part is crystalline, this part is amorphous. I think both of you agree to the fact that this part is crystalline, this part is crystalline, this part is amorphous. Now the question is, I want to see this. That is a possibility, yes. So you want to actually use very small volume mechanical property. So basically look at the mechanical property here and so on, so on. So if you can do small volume mechanical property measurement like using nano indenters, for instance, there might be some possibility of sort of determining. What else? You have seen some other properties, no, in the last class. What are the other properties? In fact, I asked you to develop a product based on something. Can you use any light? Can I just use this light? Polarized light. That's right. Because if I use polarized light, this region would look very, very different from this region. So if I look at this under a polarization optical microscope, I would essentially find contrasts. Okay, which would enable me to sort of see that this is crystalline, this is crystalline, this is crystalline, while this is not crystalline. Can you have a 100% amorphous polymer? Is it allowed? Oh, absolutely. This, rapid cooling, you will have a 100% amorphous polymer. What will happen if you do an XRD on a crystalline polymer versus amorphous polymer? So can you go to the board and then draw some? Varda, can you try? So you can erase that if you want. I'll give you the, or you can write it here because I have already written something here. So can you label your x-axis and y-axis please? And maybe I can give you a better thing. Can you draw it a little bigger so that it is actually visible? So label the x-axis, y-axis. By the way, all of you will have to do that. Make sure that you label your x-axis and y-axis and clarify whatever you are labeling on the x-axis, y-axis. So index it properly and so on, and then So this is for a crystalline system, isn't it? Now for an amorphous system, what would happen? So there will be a very broad background, a Gaussian background. Now when you compare polymer XRD with, let us say, inorganic solid SRD, okay, ceramic XRD for instance, what is the difference in 2 theta that you will find? So what are the typical 2 theta values that you see, let us say, when you work with an inorganic crystalline solid? Yeah, so here D will be very large. Here D is very, very large, so the theta can be very small. So that is why you do small angle X-ray scattering. So this 2 theta can be as little as 10 degrees for instance, and you can actually get all these peaks. But in the case of solids, crystalline solids, this 2 theta will go all the way till several tens of degrees, and that is a big difference, okay. And that has to do with the fact that the periodicity is larger in this particular case. D is larger, small d, the interplanar distance is much larger between 2 polymeric chains when compared to between 2 atoms in an inorganic crystalline solid. Do you want to explain something else? I mean, I motivated this by talking about some biological polymers also. So if you do polymer crystallography, you can actually determine the relative positions of atoms. That means that's rather interesting, and that is why I said NMR along with X-ray scattering is important to study the structure of polymers. NMR alone may not be necessarily the most effective way of doing it. You have to do NMR along with X-ray scattering. You have to keep it going simultaneously. However, this is an entire area by itself, you know, protein crystallography for instance, and protein crystallography is very widely studied and things of that sort. Now, why don't you read this a little bit? So, look at this picture. This is a optical micrograph itself, but by using polarized light. Look at this, rather interesting, isn't it? So this is by using polarized light. There is something called transmission polarized optical microscopy, alright. And what do you see? You see these regions and then you see these regions. So what do they correspond to? Number one, so you can read the caption and make sense of it, and then read this question and try to put these two facts together. So you have some data, you have some literature, and we have to stitch it together. You understand? By the way, they use a word Maltese cross, which you may not know. You're welcome to look at Google images for that. Alternatively, I can tell you what it looks like. It looks like this. So it is a cross, but it looks like this. So you can see that that's the kind of structure that emerges. So can you start discussing with one another? So you identify 3 things here which can fit into some observations you are making here. That's another way of thinking about it. Identify 3 things here which fit into some observations you are making here. You understand? Yeah. Please discuss. So can you turn to one another? So what are some of the words that you saw? Spherullites, radiates, Maltese cross. So shall we write down some keywords and maybe you can start stitching things together. So in this figure you have seen Maltese cross, you have seen spherullites, photomicrograph or polarization photomicrograph. Polarization photomicrograph, that's another keyword. Semi-crystalline, that's another word. Chain folded, so these are actually chains folded into one. Chain folded lamellae or structures. So you have chain folded structures, and the radiation, see, it can be from a common center, right? So from these maps between some of the words here and some of the words here and the picture, can you come up with some suggestions, some observations?
This is kind of linear polymer, which form in this shape.
Yeah. So it is a polymer that is actually forming lamellar structures. They are called chain folded lamellar structures because what is happening is you have these chains that are actually folding like this. So they are chain folded structures. So ribbon like chain folded structures or lamella, what are these? Interestingly, you see it's isotropic. In all directions you will find the Maltese cross. It is not only in one direction, in all directions you are actually finding Maltese cross. So it's an isotropic process. What does that tell you about the crystallization event? Is it directed solidification or is it isotropic cooling? It is isotropic. Because if you were to do directed solidification wherein you say I will cool this first, then I'll have a gradient, then I would actually have crosses for oriented in one direction. I would have crystallinity in one particular direction. So I could have directional solidification of a polymer melt, and that would change this. You would not get this kind of a polarization optical micrograph. Okay, instead you would actually have chains, the ribbon-like structures that are oriented in the direction of solidification. Now, do you have any amorphous region here? Definitely. So there are amorphous regions here. Now, such structures are very often seen with dash chains, linear chains. So such structures are very often seen with linear chains. Now, what you do is if you introduce bulky side groups here, do you think that this Maltese cross will form that easily? No. So spherulitic structures, it can be very difficult to get if you have bulky side groups, bulky side chains, steric hindrance, and so on. Similarly, if you have atacticity, in atactic polymers, in fact, reports of near 100% amorphous nature is common. So it is not unheard of. So if you look at literature on atactic polymers, you will find that a good fraction of them are near 100% amorphous. It's only with isotactic systems that you end up getting some very nice structures like this. So linear isotactic structures, when cooled, first melted and then cooled, give rise to this ribbon-like structures, lamellar structures, Maltese cross-like structures, and these structures are called spherullites. These structures are called spherullites. So the real reason for them has to do with the enthalpy of interaction between the chains. For instance, think about it. You have a chain like this, all right, and there is free volume around it. Now the question is, what will you pack that volume with? You would pack it with something with which there is a negative delta H, all right. Then there is a negative delta H, and it couldn't go infinitely straight. Because remember, this is not an inflexible chain. It is a perfectly flexible. It's basically just a set of atoms, isn't it? It's a chain of atoms. They couldn't just go endlessly. So they would have to fold. And that's really how this actually happens. So this is sort of where the process starts, and it expands because there's a template. There's a template, and so there's a spillover here, a spillover here. Next time there is a further spillover, till it reaches something like an amorphous region like this, you see, where it gets terminated. So the characteristic dimensions of these spherullites, do you think it would depend on the viscosity of the polymer melt? Yes. Very much. The more viscous the polymer melt, the smaller are the spherullites. Now, if you have large number of these spherullites, will this particular polymeric system be brittle or ductile? Brittle, because there are so many ways for you to actually just cleave it away. This could actually, you could cleave it away here, cleave it away here, and so on. So there are so many ways in which it could just come apart. So if I increase the amorphous region, can I make it tougher? So what is toughness? Toughness is the energy you have to, is a measure of the energy you have to give to a material before it comes apart. Okay, so I just told you that the system becomes more brittle when you have more and more crystallinity. That means when you have more and more spherulitic structures. Now let me increase the amount of amorphous region. What will happen to the toughness? It increases. So if I reduce the spherulitic region, it becomes a tougher polymer. I can box the polymer. So having more amorphous region basically means to say that the polymer will survive punches, will survive impact. So these are semi-crystalline structures. Can you see a correlation between this and the nucleation and crystal growth related arguments we have made in the past? So it is like nucleation, right? So there is a crystalline region that is nucleated and it's growing, nucleated and growing, nucleated and growing. So if I have anisotropic cooling associated with this melt, then will I have spherulitic structures that are radiating? No, I would have directional. So if I have more amorphous regions, I will have enhanced elasticity. True or false? If I have more amorphous region, I will have enhanced elasticity. True or false? True. Now I told you that if I have more amorphous region, I will also have enhanced toughness. If I have more amorphous region, I will also have enhanced elasticity, right? So how do I measure toughness? So toughness has to be a punch. So there are tests called impact tests. So you can write down the names of the impact tests. So there is something called the Chevron impact test, the IZOD impact test, and the Sharpie's impact test. So these are impact tests, basically providing energy to the system till the system comes apart. For example, in a Sharpie test, you prepare the sample and allow a pendulum to hit the sample till the sample basically comes apart. And the more crystalline it is, the more it will come apart, the more easily it will come apart. So do you think that improvement of toughness can be valuable for making structural plastics that are used for making structures? Absolutely. So structural plastics typically will have dash amorphous region, lower, higher, higher. Structural plastics. So if you look at structural plastics that are used in construction and so on, if you do the XRD on them, if you did the POM on them, the polarization optical micrography on them, you would find that there will be lots of amorphous region. It'll actually have as much as 70 to 80% amorphous region. It's very common for structural plastics. But if you are looking at optical systems, like the ones that I told you earlier, to make a Polaroid, which is what is called as a pleochroic system. So for making, so on the other end of the spectrum, so this is for the structural purposes. For structural purposes, I would end up having systems with very large amount of amorphous region. For optical purpose, on the other hand, what would I do? I would actually prefer this. I would prefer these crosses, and I would prefer to even align these crosses, correct? And as a consequence, in the case of optical applications, you would prefer crystallinity. In the case of mechanical properties, you would actually try to reduce the amount of crystal. Do you understand this? So it becomes an engineering parameter that you can tune. Crystallinity as a consequence has very great value from an engineering sense, because on one hand the same system could be used for optical purposes, on the other hand the same system could actually be used for structural purposes, provided you engineer it suitably. And one of the critical engineering parameters as a consequence becomes crystalline objects. Now we will close with one homework question, which is the cis-trans isomerism, because we haven't discussed that. So can you go to the board, because seems like you have done that homework. So can you erase the board, and before you erase the board, please take a picture of it, and you can share it on the class WhatsApp group, and then you can show what cis-trans isomerism is. And with that, we will conclude the class with some final concluding remarks. It is nucleation and crystal growth. It's a crystalline structure. So when you are doing XRD, for instance, where are you getting those XRD peaks from? They are coming from those spherulitic structures, that crystalline region. You understand? So usually in a polymer course you start with formulae, but in this course I have tried to avoid that and tried to bring out concepts first, and then you can add formulae on top of it on a need basis, you know. So yes, please. So this is the first time you are seeing formulae by and large in this course as far as polymers is concerned.
So we have some functional group. So this similar functional group on the same side, this is called system. And this is opposite side. So when we polymerize these things, if on polymer these groups are on the same side, it's like almost this isoelectric. But this double bond should be
right. So how will you study these polymers? What will be the difference between the two?
So generally these are more stable because of the steric region and all.
But if I wanted to study a cis population and a trans population, what would be the experimental measurable? Alright. Energy is one. Can you think about another thing in light of the discussions we have had? So there is something called racemic mixture that you have studied in your high school chemistry. So what is a racemic mixture?
But that is with the stereoisomer.
Yes.
I'm not sure.
Yes, yes, yes. So why don't you think about it? Okay. So would you consider this molecule to respond differently when compared to this molecule to polarized light? If so, why? If not so, why? Alright. How does this compare with something you have studied in your high school? Let us say racemic mixtures. Okay. So let us think about it, and that is the homework for the next class. Alright. Thank you very much. With that, we have come to the end of this particular session. So can you quickly help me recollect lessons we have learnt about polymers? So you can take out your notes. So I can actually make a ladder out of linear polymers using radical polymerization. And ladder polymers, are they harder or less? They are harder. Very good. Are they hard? Okay. And then what's another thing that you learned? What about their TG value? Higher. Very good. Next. Yeah, so we looked at DNA. I mean, it's a very, very interesting idea, right? So DNA as a polymer, and so you have some lessons to learn there. So DNA can actually condense in a remarkable manner, but there it is happening because of very specific interaction between DNA, which is the polymer that is being packed, and protein scaffolds, so that is involved. So something analogous can in principle be envisioned. In the last class we looked at polymers and the fact that secondary phases can influence nucleation, crystallization in polymers. So an equivalent question would be, and that's exactly what is happening in the biological world. The proteins are actually helping in the organization of this DNA. How can something as dramatic be done in the case of polymer engineering when you want to sort of improve the crystallization associated with polymers? I mean, what would it look like? It's an interesting problem, and I think it's almost a research problem, and you will have to think about it. Okay. Next, crystalline polymers, amorphous polymers. What are typical amounts of crystallinity that you see in a polymer? Yeah, around 40%, and it's about 60% max. So I want application wherein toughness is required. Do I need something that is amorphous, more amorphous, or more polymer? I want an optical application which involves making a polaroid or more crystalline. Does the crystallinity depend upon the kind of cooling that we do of the polymer melt? Yes. The spherullitic structures that we saw, what was happening as far as cooling was concerned? It was isotropic cooling. Will it be the same if I do directional cooling? No, I would actually have crystals that are oriented. What are some other things that you studied? XRD patterns. The 2 theta typically correspond to small angles. Small angles. To study the structure, the macromolecular structure of a protein, what are the 2 techniques that you can use? NMR and small angle X-ray scattering. So SAX and NMR will be helpful. So you have to do it simultaneously in order to understand how atoms are positioned with respect to one another. What are these regions with these folded chain structures called? Spherullites. How were the spherullites observed, or how are they observed? Yes, by using optical, most importantly polarization optical microscopy, right, or micrography. How does an amorphous system's XRD look like? Very broad. It wouldn't actually have any peaks at all, right? Next, what is the reason why these chain-like structures actually form? Chain-like folded structures form? Because of the interaction between the chains, isn't it? So, between linear chains and branched chains, which would actually form spherullitic structures more easily? Linear chains. Then I have the same composition. Can I use it in principle for mechanical application on one end, optical application on another end? So by and large the way you process it matters a great deal, isn't it? What are some other things that we discussed? Yeah, and we also discussed geometrical isomerism. There is a cis-trans isomerism, and you also have a question as a consequence. What is the question? How would you study them? How would you determine the cis versus the trans configuration, and what implication does that have as far as monomer choice is concerned and polymeric systems are concerned. So those are your homework questions. Not really, not when you take it out of the cell. In the cell, it is actually something called condensed DNA. It is condensed DNA. So it is so well ordered. It's so very well ordered. So that's why I told you biologists don't like to use the word crystallization, except if they actually extract it and then do slow cooling and crystallize the DNA to get good XRD signals. And they also use this combination of SACs and NMR in order to study proteins, DNA. DNA crystallography is an area by itself. Protein crystallography is still a very active area of research because there are so many proteins in the biological system. In fact, there are PhD theses on crystallization of one and study of one protein because it's so hard. Just one system, okay. So nowadays things are becoming better. Now there are things called protein databases, so that people use, where they use this idea of something called putative proteins in order to understand crystallography. And as far as the pedagogy is concerned, we discussed a couple of things. Would you want to actually recall some of the pedagogical things that we discussed? Learning actually helps in creating scaffolds and in order to do assimilation and accommodation, right? Socratic learning is helpful. Next, yeah, Hackness tables. You know what you are doing right now is Hackness table. What's another thing that we discussed? And in fact, when I asked him to take a picture and send it via WhatsApp, that was an example of connectionism, because I'm making sure that there is some classroom interaction even beyond the classroom. And that means you are engaging in classroom content even beyond the classroom. So there is that connectedness that is helpful for learning. What's another thing? Piaget's ideas on constructivism, assimilation, accommodation, and so on. What's another thing that we discussed as far as pedagogy is concerned? Note making being a very specific skill, and as I told you, if you are interested in reading about it, you can look at the Feynman's technique and the Cornell note making. These are two very widely taught methods for note making. What's another thing? Introverted students, yes, that's right. So it's a puzzle how to sort of make introverted students perfectly comfortable in a active cooperative learning setting. I think a big part of it is just sensitivity on the side of our fellow students and also of the teacher, and also utilizing one-on-one interaction could actually be helpful. Reading interventions and basically valuing it as equivalent to classroom interaction might be ways in which you could actually leverage this. And I also gave the reference of Susan Cain's book, which is a rather recent one. It was published, I think, only in 2017 or so. So it's available on Amazon and so on. Thank you very much. With that, we are done with this Swayam session. So see you all soon. Thank you.